So now we'll do some exercises based on graph theory in Sage. Okay, so I have 3 exercises. You can select whichever one you want. One is based on algebraic connectivity. So if you don't know the definition of algebraic connectivity, it is the second smallest Laplacian eigenvalue. So if you take a graph, for example, we take a random tree for now. Okay, let me take a random tree on 6 vertices, and no, yeah. How do you get the spectrum of G? Do you recall? G dot spectrum. So I think I did not show you the Laplacian spectrum. So if you do G dot spectrum, what you get is the adjacency spectrum. Suppose you want the Laplacian spectrum, the eigenvalues of the Laplacian matrix. So here you just have to change it or add an optional argument, Laplacian equal to true. So even if you type this much and tab complete, it comes Laplacian equals true. Now what you get is the Laplacian spectrum. As you can see, 0 is an eigenvalue, because for the Laplacian it's always an eigenvalue. And if the graph is connected, then what will be the multiplicity of 0 as an eigenvalue of the Laplacian matrix? 1, right? The graph is connected if and only if 0 is a simple eigenvalue of Laplacian matrix. So the second smallest eigenvalue, 0 is the smallest one because it's positive semi-definite. Second smallest eigenvalue is something called the algebraic connectivity of the graph, for any graph, not just tree, any graph. Okay. So if the graph is not connected, what will be the algebraic connectivity? 0, because 0 will not be a simple eigenvalue, so the second smallest also will be 0. Second smallest when you consider all the eigenvalues, not only distinct ones. You are considering the entire spectrum, the multi-set, and the second smallest will be 0 if the graph is not connected. So that itself indicates that it has something to do with connectivity, correct? And in fact, lots of studies have been done which show that it is very closely related to the connectivity, and it is a better measure of connectivity than vertex connectivity or edge connectivity in many cases. Because if you take a tree, the edge connectivity is, if you take any non-trivial tree, the edge connectivity is always 1, because every edge is a bridge, right? But if you take a star or a path, you can say that if you consider these as networks, one is certainly better connected than the other. For example, in a star, if you delete one vertex, it is not only becoming disconnected, it becomes totally disconnected. Whereas in a path, if you delete one vertex, if you delete one internal vertex, it is getting disconnected into 2 connected components, 2 trees, right? So in some sense, the path has better connectivity. So the algebraic connectivity measures that to a certain extent. So lots of theoretical studies have been done. You can read the papers. So how to find the algebraic connectivity of a graph? Get the Laplacian spectrum and find the second smallest eigenvalue, the one before 0. So again, if it is not connected, that is 0 itself. You don't count distinct eigenvalues. Take all the eigenvalues and then find the second smallest one. So write a small function to find the algebraic connectivity of a given graph. That's not the entire exercise. So the first part is write a function to find the algebraic connectivity of a given graph. So this will be a very small function. Okay. Then suppose you are given a particular order n. Okay. Find the tree of order n having the largest algebraic connectivity among all trees of order n. Is that clear? So given a particular order, Maybe I need to zoom in a bit. Is it visible to everyone? Right. So, given a particular order n, number of vertices n, you have to get all the trees of order n, find all their algebraic connectivities, and find the one with the largest one. Okay. So obviously you will be using the first function that you wrote for this thing. That is an efficient way rather than writing everything in one function. And maybe you will have to write some other helper function as you judge. Right. Maybe something else you want to write as a separate function. So that's one problem. Is this clear? This is, as I said, it's optional. If you want, you can do this one or any of the other two exercises. So another definition. That's a Steinhaus graph. So Steinhaus graph is defined in this way. Let me show you the definition carefully. Suppose you're given a vector A. Okay, here I'll write it as a list for now. 0, 0, 1 vector A. So for example, 1, 1, 0, 1. Okay. You know that adjacency matrices of graphs are symmetric 0, 1, 0 diagonal matrices. Right. So now given any 0, 1 vector as a row vector, for example, I am going to generate an adjacency matrix from this in a particular way. So given one row, I can generate an entire matrix using a particular procedure, and that will define a graph. We'll generate it in such a way that you get a symmetric 0 diagonal matrix. So what I do is, here I will manually do it and show you. As first row, I will take the given row with a 0 appended at the beginning. So I am appending a 0 in every case because I want a 0 diagonal. I can't have my first entry as 1. I don't want self loops. So whatever the given vector, append a 0 right there. So this is the first row. Okay. Now for the second row, the first entry should be a symmetric matrix. So the first entry should be whatever is the second entry of the first row. So that is 1. Second entry should be 0. Okay. So these two are determined by the first row itself. Now for the third entry, you see these two entries below it. If you remember Pascal's triangle, how you construct Pascal's triangle, this is somewhat similar. Okay. If you see these two entries, add them modulo 2. So consider them as entries in the field of order 2. So 0 and 1 are the things, and 1 plus 1 is 0, 1 plus 0 is equal to 0 plus 1 equal to 1, 0 plus 0 is of course 0. So add them modulo 2 and write the answer here. So 1 plus 1 is 0. Right. That is the third entry. Similarly, this entry will be 1 plus 0, which is 1, and then 1. Yeah. Now again, if you see that the lower triangular part is completely determined by the upper triangle. So the first 3 entries here are already determined by these 2 entries and 0, right? So 1, 0, then the diagonal will be 0. So 1. So here I am not doing that computation. I am making it symmetric. I am writing it in such a way that I get a symmetric matrix. Now the computation. So what do you get? 1, 0. Similarly, 0, 1, 1, 0. That much is determined. And now 1 plus 0 is 1. Now 1, 1, 0. I look at the last column and write. And of course the last entry has to be 0. Again, no additional computation, is just that. Is this procedure clear? So here, I will name this matrix as A. And I have previously shown you how to get a graph from an adjacency list given as a dictionary. Also how to get the adjacency matrix of a graph you can do it in the reverse also. Given a matrix, you can get the graph corresponding to the matrix. So I'll say G is equal to graph of A. Maybe I'll use a circular layout so that it's plotted nicely. Okay, this is the graph. Maybe I'll use. Zoomed in. Yeah, right. So this is the graph. So as you can see, this is the entire computation was based on the given binary string or 0, 1 vector. It's basically a binary string. Right. So always start by appending a 0. Even if the first entry is 0, start by appending a 0 and then do this. So the exercise is given a 0, 1 vector, generate its Steinhaus graph. Well, write a function for this, of course. Yes, you have to, because that is the definition. The definition is that. Otherwise, you will not get all possibilities. So let me ask, if the vector is of length n, what is the order of the graph you get? N plus 1. That has to be kept in mind because you are always appending a 0. Okay. Fine. So as I said, you can pick any of these. And lastly, if you know the blocks and cut points of graphs, let me take an example. So I'll use sorry about that. Maybe I'll copy a graph from here. Yeah. This happens to be a friendship graph, that's fine. So if you know about the blocks of a graph, you can see that there are 4 blocks in this graph, okay, and 8 is a cut vertex. So blocks are nothing but maximal 2 connected subgraphs of a graph. Okay, so that means graph is 2 connected if you have to remove at least 2 vertices to make it disconnected. A connected graph is said to be 2 connected if you have to remove at least 2 vertices to make it disconnected. It is not that if you remove 2 vertices it will definitely become disconnected, but removal of 1 vertex will not make it disconnected. That is the definition of connected 2 connected graph. Okay, if it is connected. Fine. So a block is a maximal 2 connected subgraph. Even if you think the definition is a little difficult, intuitively it's very easy to see. These are the blocks of this graph. This 803, then 865, then 824, then 871. You can see that how they are blocks, right? Maybe I'll generate another graph. So yeah, here the blocks are, again there are 4 blocks. 4,5 is 1 block, 3,5 is 1 block, 1,5,6 is 1 block, and 0,25 is 1 block. Okay. this is a tree. In a tree, every edge forms a block basically. Okay, this is a better example. Okay, here again there are 4 blocks. That's because I've asked it to give me 4 blocks. There are 4 blocks. 3 7 is one block, 0 2 7 is one block, 7 5 6 is one block, and 1 4 6 is one block. So I hope intuitively at least you understand blocks. I don't remember this function, how it works. 4 is definitely the number of blocks. Okay, 2 3, yeah. Okay. Best way is to check the documentation. As I said, you cannot remember everything. At least I cannot remember everything. So I'll check the documentation for what exactly it is. This is okay. This is just a function to give you a block graph for the sake of checking this. Okay, so while that generates, I'll continue explaining. So these are the blocks. Now, you have learned about the incidence matrix, which is actually the edge incidence matrix of a graph. In general, in combinatorics, there is something called incidence structure. So that's where you have 2 different sets of objects, and you have some relation between these 2 sets, which is the incidence relation, which you call the incidence relation, saying that elements of one set may or may not be incident with elements of the other set. And so whenever you have an incidence structure of this form, you can generate an incidence matrix just like the edge vertex incidence matrix. So in the case of the normal incidence matrix that you have studied, the one set is the set of vertices of the graph, the other set is a set of edges of the graph, and you say that an edge is incident on a vertex, or vertex is incident on an edge if that vertex is one of the end vertices of the edge. So that defines the incidence relation. Similarly, if you have a block, if you have the blocks of the graph, you can take the set of blocks to be one set. So here 7 3 0 2 7 etc. 1 4 6, these are the 4 blocks of the graph, and the vertex is incident on a block if it is one of the vertices of that block. So 7 2 and 0 are all incident on this block, or you can say this block is incident on 0, incident on 7, incident on 2. Similarly, this block is also incident on 7, but incident on 3, not 0 and 2. So similarly, you can define incidence relation. Now you can get a matrix from this, and you can study it just like you study the incidence matrix of a, or vertex edge incidence matrix of a graph. Okay, so this is not already defined in Sage. So you have to write a program to get the block incidence matrix of any graph. For that, you have to identify the blocks first. You don't have to write an algorithm for that because that requires more graph theory. Sage has a function which gives you the blocks, but you have to get these blocks as a set or as a list and then generate the matrix from this. Okay, let me look at what this function does since you asked. K and K max are, so block is a, yeah, this is the number of blocks. K max is probably the number of vertices, maximum number of vertices in the block, right? Yeah, okay, that's it. So this K is the minimum number of vertices in the block, and K max is optional. It is the maximum number of vertices in the block. So if I want to quickly, if I randomly generate a graph, probably you will get a graph which is entirely one block. So for example, if you take this, because you have these cycles here, okay, the entire graph is one block, so I'm not getting an interesting structure. It's like if you're considering the incidence matrix and you take a graph with only one edge, so it's as bad as that. Here there is only one block, so you won't get an interesting structure. So I want something where there are some number of blocks, so I can generate this. This was just for checking. So once you understand this, the task is clear the output, that's okay. Write a function that generates the vertex block incidence matrix of a given graph, any given graph. Okay. Okay. So the rows of this matrix should be indexed by vertices, just like the vertex edge incidence matrix, and the columns should be indexed by blocks. Okay, maybe I can show you an example. Alright, I need to write it down. Yeah, this is a very large graph. Okay, in this okay, so this is the block graph generated here, and this is its vertex block incidence matrix. It is 0, 1. It's not 0, 1, minus 1 because there's no natural way to give any orientation to blocks. So this is the graph in this case, and this is the matrix. Since there are 4 blocks, it has 4 columns, and number of vertices is 7. Okay, so yeah, there are 7 rows. Okay, as you can see, there may be 3 non-zero entries in a row. That's because there are 3 vertices in the block. So it is again not like the incidence matrix where you have exactly 2 non-zero entries. You may have any number of them depending on the size of the block. So you can see that a lot of information is there in this about the block structure, which is that the number of ones in the column gives you the number of vertices in the block, and the number of ones in a row give you how many blocks the vertex is incident with. Right. So this is the first row, 0. 0 is not a cut vertex. It is non-cut vertex. Therefore, it is incident with only one block, and so on. Okay, so this is the example. You should write this program. This is the third task. So you can do any one of these. So I think for this you might need a function to get you the blocks of the graph. So here, alright, not G. Here, this is a very helpful function. You can use this. As I said, you don't need to use graph theory knowledge to find the blocks. Sage will do it for you. So this gives you the list of blocks and cut vertices here. As you can see, the first one is a list of lists. Each list gives you the vertices in that block, and this is a tuple of which the second component is simply a list of vertices, which is nothing but the cut vertices, here 8, 0 and 7. So this is the information you need. So using this, write a function. Is it clear?